Our chapter 14 is discussing chemical equilibrium. I notice on the opening slide here is a heart valve or a blood vessel in which you have an equal amount of blood vessels heading in as out, an equal but reverse process. Chemical equilibrium begins to explore reversible reactions. Many of our topics have included when a chemical reaction proceeds, we only think about it as heading in one direction only, where the reactants turn to products and it goes to completion, end of story. But oftentimes, as products begin to accumulate in their concentration, these collisions can increase in frequency, and we can see a reverse process beginning to achieve going back to the original reactants. This is the topic that we will begin to explore in Chapter 14, Chemical Equilibrium. So to look at a reversible reaction, we talk about arrow conventions. In a forward reaction, we often use a single arrow for reactants going to products. But as more and more products begin to accumulate, we start to see the reverse reaction occurring as well. So we have a forward arrow and a reverse arrow, and oftentimes you'll see those written as a double arrow in these sets of notes. When I handwrite them, the forward and the reverse reaction each going in the opposite direction. So one direction only is a not reversible reaction. When we see double arrows, it is indeed a reversible reaction. When a reaction starts, the reactants are consumed and products are made. So at the very initial moment in time, the only direction would be the forward direction as reactants create products. Therefore, the reactant concentration decreases and the product concentrations will begin to increase. Reactants get used and products get made. As the reactant concentration begins to decrease, the forward reaction rate will eventually slow down as well. Eventually, we'll see that the products start to react and reform some of those original reactants. And we see that as a reverse reaction, where the products go back to the original reactants. Assuming the products are not allowed to escape the vessel, and as that product concentration begins to increase, the reverse reaction rate will increase. The processes that proceed in both the forward and reverse direction are said to be reversible. Where reactants form products over time, products will go back to the reactants. We have a forward and a reverse reaction occurring at equilibrium. Suppose in this particular set of data, the reaction has two red forming a blue, and that's just generic chemistry, the hypothetical reaction. The reaction slows over time, but the red molecules never run out. At time 0, we have only red and no blue. As the reaction proceeds, the concentration of the red slowly decreases until an equilibrium is reached. The blue slowly increases until an equilibrium is reached. So over time, the red decreased, and over time, the blue increased. Notice at equilibrium, it does not mean that the concentrations will be the same. It does not mean that they are equal in amount from red to blue, but the forward reaction is occurring at the same rate as the reverse reaction. That's the meaning of equilibrium. The forward rate of red turning into blue is at the same rate as blue going back to red. The forward rate and the reverse rate are equal at equilibrium. Forward equals reverse, not in concentration, but in the rate at which the reactions occur. Graphing what we had looked at in terms of a data table, at time 0, again, this isn't showing, but at time 0, we would have no blue, but over time, equilibrium is achieved. At time 0, we have all reactants, and they got used as time went by. Products got made, reactants got used until we see the flat line where equilibrium has been achieved. Notice that in this particular graph, the words are overprinted, so let me explain what's going on. If the rate versus time is plotted, we see that at time 0, there are no products. Products began to increase. This would plot rate versus time of the reverse reaction. Of course, the forward reaction starts with all reactants turning to products, and reactants get used until an equilibrium is achieved. So where the lines converge together, we have equilibrium, where the concentrations remain constant, not equal to one another, but a constant amount. As the forward reaction slows and the reverse reaction accelerates, they will achieve a dynamic equilibrium, wherein the rates of the forward and reverse reactions are equal. Once the reaction reaches equilibrium, the concentrations of all the chemicals will remain constant because those chemicals are being consumed and produced at the same rate. If hydrogen and iodine combine to make hydrogen iodide in a 1:1:2 ratio. At time 0, there are only reactants in the mixture, so the only way we can make a reaction occur is in the forward direction. Let's suppose the concentration of hydrogen are 8. 1, 2, 3, 4, 5, 6, 7, 8 molecules. We have hydrogen giving those little smaller molecules here, and the iodine would be the larger, and they are also 8. And in this first picture at time 0, there are no products. We allow that reaction to proceed. At time 16, there are both products and reactants. Now in this picture, I'm counting 6 hydrogens, little ones, 1, 2, 3, 4, 5, 6. There are 6 iodines, 1, 2, 3, 4, 5, 6. And then 4 HIs, one of each in here. So not the same amount, but we have indeed achieved an equilibrium where the forward and reverse reaction are occurring. So at the same rate, H and I collide to make hydrogen iodide. At the same opportunity, this then decomposes back into the original reactants. Still more time.